Thank you so much. Okay. All right. I think this is where we left off, yes, last time. So let's pick up and go from there. All right, any questions before we get started today? If you've got your book, this is on page 262, chapter 4, section 4.2. Chapter 4 is integration, 4.2 is area, and this is finding area by the limit definition. Okay? And we'll try to go through this fairly quickly because I don't do anything quickly. Okay. Let's consider a plane region bounded above by the graph of a non-negative continuous function, such as this one. Now, we can't do it back here because here the function goes negative. But from A to B is all non-negative from A to B. You can go past B and still be non-negative. Yeah, a little bit before A and still be non-negative, but you can't go past here. So basically, keep the function positive. Okay? Continuous function. You can't have any gaps, holes, anything in it like that. Okay? The region bounded below by the x-axis, on the left and the right by x equal A, x equal B, okay? And then on top by the function itself. What we're looking for is the area of that region under the curve, okay? Now, you might say, why? But hold off on that. You'll see plenty of reasons later. Huh? 262. Top of page 262. All right. Now, we're going to blow this up a little bit. Okay. And then we will talk about how we're going to find that area. It's not much of a blow up, but a little bit. To approximate the area in the region, we're going to begin by subdividing the interval from A to B into little sections. Okay? And we're going to call those delta x's. Now, how are we going to do that? Well, we decide how many of those little sections we want. Oh, we want n of them. Whatever n is, whatever number that is. So what we'll do, we'll take this length from A to B, and how long is that? B minus A. That's that length. Okay? Divide it by n. How many sections we want? 3, 4, 5, 6, 7, 8, 11. Okay? 11, 12, maybe. Okay? 12. So divide by 12. So each one of these is that length, B minus A, divided by 12. That's your delta x. Okay? Change of x. Delta, difference in x. From x here to x there, that's your difference in x. Okay? Now, that interval is subdivided into that many. So let's just look at this one here. This, we'll go up here and I'm betting this is Vince. Yes. All right. The reason is you're the only one that wasn't here. Okay. Now, perfect attendance 3 days in a row. Way to go, team. This is the best class ever. Okay. Now, how we're going to estimate the area under this curve is using a rectangle, which is not a very good approximation. But it's okay. It's not bad. We could take the first side here and make the rectangle this way. That's the maximum, you might say, the big M. And that overestimates the area under the curve by that little blue amount there. Or we could take this alpha of M on the low side and do that rectangle, length times width, but this length times that width. And that would give you an underestimate by that little sort of semi-triangular looking area there. Okay? So that would be an estimate. How could you get a better estimate using the same technique? Smaller, take more n's, smaller delta x's. In other words, if you had a delta x half that size, then those two rectangles are going to come closer to fitting the area there. And you keep doing this until your delta x is approaching 0. And that's the limit. Right? So that's how we're going to do it. That's the general idea. Easy to do the area of a rectangle. Length times width. And the width is always delta x. The length could either be the long side or the short side. doesn't matter. You're going to keep going smaller and smaller rectangles until basically you have one so thin you can estimate exactly what that is, because look, it's like only one value there. Okay? So that's the approach. So the endpoints of the interval are, the A is at x0, which is A plus 0 times delta x. In other words, it's the A of x0. A plus 1 times delta x, that's the second one, that's your A sub 1. And then 2 would be your x sub 2, like that. And finally, the last one, when you get into those out there, you're all the way to B. Okay? So you add some I delta x there to your A. Because f is continuous, the extreme value theorem guarantees the existence of a minimum and a maximum on each subinterval, no matter how many subintervals you got. So the f sub mi would be the minimum value of f of x on that interval, and f sub m capital Mi would be the maximum value. They don't have to be the endpoints. They could be some point in between, but there's some minimum and maximum there. Okay? Next, we define an inscribed rectangle lying inside the ith subregion, and also a circumscribed rectangle extending outside the ith one. The height of the ith inscribed would be that minimum value that's going to be totally inside under the curve, and the height of the circumscribed one is going to be that maximum value that's going to be the height of that one. Therefore, for each I, the area of the inscribed rectangle is less than or equal to the area of the circumscribed rectangle, but guess what? In between the two is the area under the curve. Okay? So you could put another one in here. Area of inscribed will be the function value on the minimum side times delta x, and on the maximum size, function value there times delta x. This will always be less than or equal to that one, and then the actual area is going to be something in between those two. Equal to or less than in between those two. Okay? So the sum of the areas of the inscribed rectangles is called the lower sum. The sum of the areas of the circumscribed rectangles is called the upper sum. Boy, that sounds exciting, doesn't it? Okay? So the lower sum will be the sum of the summation I equal 1 to n, however many little subdivisions you have, f of all of the minimum values on that subinterval, okay, times delta x, and this will be the sum of all the maximums, the area of the circumscribed rectangle, which would be summing all those together. That will be a minimum, that will be a maximum, okay? So here's how it's going to wind up looking. From this figure, you can see that the lower sums will be less than or equal to the sum of this. So lower sum, here it happens to be this endpoint, that will be that endpoint there. This will be that one, this will be the other endpoint, that one. This actually would be some point in between that's inscribed under all. Here will be this endpoint. But you see, all these rectangles are going to be less than the area under the curve, because you always, that meets it every time. But the circumscribed rectangles will then be the maximum value, and this one actually will be some values awfully close. This one will be that value like this one will be that one. So these always overestimate, and the curve is somewhere, the area under the curve is always somewhere in between the two. So that's what I was saying before. The area of the region is always in between those two sums. Pretty exciting stuff, isn't it? All right? Now, here's example 4. Find the upper and lower sums for the region bounded by the graph of f of x equal x squared and the x-axis between x equals 0 and x equal 2. Okay? Now, how you do this is first draw your figure. Okay? Get my pen set up. Okay. So this is a good old parabola, and it's only going to be positive values here. So we'll do 1 and 2, And we know 0, 0 is going to be there. And we know the maximum out here is going to be 4. So this has got to be 4. So this will be 2, that will be 1, and that will be 3. Okay, obviously my scale's not right. That's 0, 1, and 2. I've got different scales for X and Y, but that's so we can see it better. So 1, 1, and 2, 4. So it does something like that. Okay? So find the upper and lower sums of the region bounded by, don't draw too well, sorry about that. Okay. Now they don't tell us how many okay, they're not going to tell us. Okay, we're going to do it for n subdivisions. So what's going to be our delta x? That's where we start. Remember what the delta x was? B minus A over n. Right? B was 2, A was 0. We're going from 0 to 2. This is your A, this is your B. Okay? So it'd be 2 over n. And we don't know what n is. However many subdivisions you want. 1, that's not going to be very exciting. 2, a little bit better. 3, 4, 5, 6, whatever you happen to choose. Okay? Now, here's something going on here. Because this is a strictly increasing function between 0 and 2, we call it monotonic, increasing totally. Okay? Because it is, then the right-hand endpoint is always going to be the maximum. The left-hand endpoint is going to always be the minimum. Because it's increasing. Okay? So this will be fairly easy to pick out. That's your delta x. So your x sub 0 is equal to 0. Okay? Your x sub, and I'll just do some arbitrary divisions here. And your x sub, we'll call this x sub n minus 1, and this x sub n, no, not n, I minus 1, x sub I. Okay? In other words, here will be the rectangle here. Your superscribed rectangle will be here. You want a different color for inscribed? You pick a color. Pick a color. Huh? Blue? Light or dark?
Green.
Green. Light or dark?
Dark.
Dark. Okay. We'll do. Okay. Yeah, the y values are here, and that will be f of x of I minus 1 will be here. F of x I plus 1 will be there. X of I will be there. Okay? So this will be f of x I minus 1, and this one here, and let me get that back to dark. This will be f of x of I. Okay? I minus 1 f of x of I. Okay. Probably should have done the green all the way across. Okay. So, yeah, that's the y value. Is the f of one of those endpoints. This will be the lower one. This will be the upper. Okay. This overestimates that one. This one underestimates that one.
Except for the delta x equation. A and B, will B be the y value, the greatest y value?
Okay.
B minus A.
The A is the minimum x value, 0, and the B is your maximum x value, 2. Okay, so that last one there, f sub n, that last one is going to be f of 2, which is going to be 4. We know that one already. And this one down here is x of 0, which is going to be 0. You plug it in there. But these others, you're going to plug in whatever value this is. Now, I is going from 1 to n, so this one up here is going to be, let me get my pin back. This is going to be x sub n, which is also, which is b, which happens to be 2. That's your x value, and there's your f, and your f of x sub n, which is f of 2, is equal to 4, because 2 squared is equal to 4. Okay, does that make sense? The height of the rectangle is your function, and the the width of it is your delta x. So this is your delta x, and this is 2 over n, whatever your n happens to be. All right. Now, yes, ma'am. Just a second. Wait, let me. You can imagine doing that. We'll see it's way easier than actually plugging in that many values, but we'll see. Okay. So here's the setup. Now, and this is they go through so much mess, and rather than me draw it and then show you how they draw it, let me just show you how they draw it. I was trying to illustrate and then we got interrupted, so let me just short circuit this a little bit and watch how they do it. Okay, we already did this. To begin with, the partition the interval into n subintervals. The interval is going from 0 to 2, x equals 0 to x equals 2. Divide that by 2 minus 0 is 2, divided by n. B minus a, 2 minus 0 divided by n is 2 over n. We did that. So that's going to be the delta x. That's going to be each little subinterval. Okay, now we're going to inscribe the rectangles. Now they're choosing n equal 1, 2, 3, 4, 5. Okay? It doesn't matter what the n is. Okay? They're using that. Okay? The inscribed rectangles is going to be the minimum. Now this one is going to start at 0. So that rectangle has height 0, width 2/5. 2 over 5. Because 5 rectangles, the n is 5. Okay? So 0 times 2/5 is 0. This one is going to be, the height of this is going to be, again, with this one being 5, this will be 2/5, 4/5, 6/5, 8/5, and 10/5 is 2, right? So that's your interval, okay? Oh, and the first one is going to be, so this is your B, and this is 0, that's your A. So that's your first one, okay? So for the second inscribed, the first one, 0 times 2/5. The second one, the delta x is still 2/5, the difference between those two. But now your max is going to, your min value here is going to be 2/5. So you'd be 2/5 squared. That would be 4/25. So 4/25 times 2/5. This will be 16/25 times 2/5. That will be 36/25 times 2/5. This will be 64/25 times 2/5. That's going to be your inscribed rectangles. Okay? Your circumscribed rectangle, you're going to take the higher of these two ends. So this will be 2/5 times, 2/5 squared, that would be 4/25 times 2/5. Exactly what this one was here, this one is there, right? So that would be 4/25 times 2/5. This one's 16/25 times 2/5. This will be 36/25 by 2/5. This will be 64/25 by 2. And this one will be 4 times 2/5. Okay? That would be that rectangle. Okay? So those are your areas there. Okay? Or those are your rectangles. And then this is doing what I just said, except it's doing with all the eyes and that kind of mess with it. The lower end point is going to be, the first one's going to be 0, and then it's going to be I minus 1 over 2 over n. And so for the i's 1, 2, 3, 4, and 5. Okay? So this will be, the first one will be 0 times 2/5, the next one will be, yeah. So it's exactly what I would call it, but 2/5, 4/5, 6/5, 8. This is how you say it. This one is going to be, this is going to be 0, 2/5, 4/5, 6/5, 8/5. This one's going to start with the 2/5, 4/5, 6/5, 8. You know, it's doing that. Whatever your counter here is, you do one less than the counter here times 2 over n. You do the counter here times 2 over n. This is the same thing where the 2 over n was the 2/5, and then that was the counter. Each one that you're doing. That's your value for your m's, which we just did. This is 0, 2/5, 4/5, 6/5. That's 2/5, 4/5, 6/5, 8/5. Okay. The i's going from 1 to n. So the first one, let's see, there's Dr. Bryant right there. Okay. Now, the sum of those is going to be these values, the f of, and that was what I did. I squared the 2/5, squared the 4/5. So that was taking the f of that, because that's your f of x is x squared, times your width of that. And that gives you this. Now, for the lower one, you plug in this value, and for the upper one, you plug in that value rather than this one. This would be an I here. Okay. And it's so much easier to actually plug in numbers than to use all these, but they're using all these. So, okay. So what is f of this number here? It would be that number squared. So that would be 4 over n squared times this squared. Okay, times that. So they can make it look so confusing, but it's a fairly simple concept. Okay, so the 4 over n squared times 2 over n would be 8 over n cubed. So that's where they got that part, and then they just squared the next one. Okay, and that's going to be the same, summing them all up. So this is actually not part of the summation. Pull that on the outside, then you do this. Well, then you have those things that we did at the very beginning. Remember? When you did the summation, the I squared was n, you know, they had, go look them up. But those are exactly those terms that we had before. That's the 8 over n cubed comes on the outside. The summation of I squared minus 2 times the summation of I plus the summation of 1. Remember, this is just going to be n here tonight. This is going to be 2 times I don't remember that one, but it's pretty simple. 2 times n plus 1. Okay. So the I squared was n times n plus 1 times 2n plus 1 over 6. This was, the I was n times n plus 1 over 2, and this is just n. And when you do all that, which is, what a pain in the neck, but it's there, it's doable. Multiply these, multiply them, multiply by the, here the 2's go out, that's going to be pretty simple. And when you do all the math, don't want to drag you through all that math, but when you do it, this is what it turns out to be. And again, sort of, take our word for it, this is it. If you want to do the math, I will. You know, we'll see. That becomes this. Okay? Now, When you get to this point, though, things get to be a lot easier. Okay? Let's take a term at a time. Let's distribute this across. That would be 8n cubed over 3n cubed, right? That first term. Now distribute this way. Minus 12, well, let's see. We'll just cut this out. That would just be doing a few shortcuts here. The 3's will go out, and that would just give minus 4n squared over n cubed, right? And the last one would be plus 4n over 3n cubed, right? Now, when you really think about this, those go to 1, right? This goes to 1 over n, and this goes to 1 over n squared, right? So this will become 8/3 minus 4 over n plus 4/3 times 1 over n squared, okay? Now, what are we going to do? We're going to let these n's go to infinity. Go to 100. That's what you want it to be, right? Yes.
Why you didn't write 3n squared in the number?
I could. I just wanted to separate it. Yeah, you could write 3n squared. That's fine. I was doing it for a reason, and maybe you'll see the reason later. Whoops. Okay. That's fine. Any way you want to write. Okay. But what are we going to do? We're going to let n get bigger and bigger and bigger, so our delta x gets smaller and smaller and smaller, right? Like we want to go to 100. So let's do this. 8/3 minus 4 over 100. That would be 0.04. So 8/3 plus 0.04, minus 0.04, plus, and 100 squared would be 10,000. Okay? So that would be 4 over 30,000. Well, 4 over 30,000 is a minuscule little number. And really 4 over 100 is a pretty small number. Well, let's get n even bigger. Well, this gets even smaller, that gets even smaller. What do you wind up with? Those are both going to zeros, and you get 8/3. That's the point. That's the only thing that's worthwhile that's left. As n gets bigger, those disappear, but you lost your n's here because they canceled out. So there's your answer. There's a limit of 8/3. Okay? Now, you can do that from the big side, and you're going to get the same result. Okay? This one has a minus, that's going to have a plus. Okay? So, whoops. Let me clear my writing out of the way. I'm trying to do it quickly. That's exactly what we got, and that's how you wanted it. That's the form you wanted it in. It's exactly what we got. That's the lower sum. Okay? Using the right endpoints for the upper sum, that would be f of 2i over n. That's going to be 4i squared over n squared. Okay? And that's what we got there. So that's going to be 8n cubed, because it's 4n squared over 2 times 2n squared times I squared. The 8n over n cubed is going to come out front. That's just going to be summation of I squared. And summation of I squared is just that simple form there, because you don't have those other two terms. But when you do all that to it, you get that same, it's not the same thing, but you're going to get something. And then this is going to be, I think I said before, the other was a minus here, this is going to be a plus, whatever it is, and that's going to be here. And when n gets very, very big, that goes to 0, that goes to 0. You're left with 8/3. So guess what? From the upper side or the lower side, you're going to 8/3 as n goes to infinity. So who cares which side you go from? As n gets big enough, you're going to the same sum, 8/3. Okay? Now, I raced through that, and hopefully you won't need any more of this. Let's look at this theorem. The next theorem shows that the equivalence of these two limits is n approaching infinity of the upper and the lower sums is not mere coincidence. It's true for all functions that are continuous functions. You can't have any gaps in them. If you have gaps, everything falls apart. And you want them to be non-negative. You've got to always be up here above the x-axis. So as long as those two conditions are met, the limits of the lower and the upper sums let f be continuous and non-negative on the interval a to b, then the limits as n approaches infinity of both the lower and the upper sums exist and are equal to each other. That is, the limit as n approaches, see, there's the key. As n approaches infinity, that's going to get smaller and smaller and smaller, so the difference between the f is going to be getting smaller and smaller and smaller. It's going to 0 too. So it's not going to matter which one you use. The limit of the lower sum and the limit of the upper sum, there's going to be the limit of the sum. Okay? Where delta x is b over a divided by n, as long as you let that n go to infinity, this thing is going to shrink down. F of m sub I, f of capital M sub I, minimum and maximum values on that subinterval. It really, see, because you're letting n goes to infinity. And when you get a very narrow thing, what's the difference in the upper and the lower? Minuscule. So they are going to the same limit. Got to, okay? As long as they're continuous function. So in that theorem, the same limit is obtained for both the minimum and the maximum. So it follows from the squeeze theorem, okay, theorem 1.8 way back then, that the choice of x on the ith subinterval does not affect the limit. Pick an x, any x. Doesn't have to be the max, the min, or any. Just pick an x, any x. So if this is your lower, that's your maximum. Yeah, it doesn't. Oh, okay. These are three different functions. Sorry about this. This is the squeeze theorem. Repeat it again. Sorry. If h of x is always less than or equal to f of x, but f of x is always less than or equal to g of x, for all x's on some open interval containing c, except possibly at c itself. C itself, it could be different. Then if the limit as h approaches c, as x approaches c of h of x is L, and that's also the limit as x approaches c of g of x, if both of them are at L, no matter which way you're going there, then the one in the middle has to be, that limit has to exist and it's equal to L. Outside those, anything could be happening. But in between, if these two limits are the same, that's the same. So our limit on the integral is going to be the same. All right. It means that you're free to choose an arbitrary x value on the ith subinterval as shown in the definition. So all that stuff about endpoints, max, min, it doesn't matter. Pick any point in the interval, okay? If f is continuous and non-negative on the interval a to b, the area of the region bounded by the graph of f, as long as it's positive, the x-axis and the vertical lines x equal a to x equal b, just like we did before. Now we don't have to say, well, I'm going to put this in or that in. Pick any value, as long as it's something in between x of I minus 1 and x of I. Any value, ci, any value there. The area as a limit, the area is the limit as n goes to infinity. There's the key. As n's going to infinity, this thing's getting smaller and smaller and smaller, and you're going to focus in, you're only going to be at c, okay? F of c sub I times delta x, where the c sub I is always in between the two endpoints. No matter how close they're getting, it's always in between the two. The delta x is that b minus a divided by n. So the width of that ith subinterval is always that. And it doesn't matter what value you use for that c sub I, as long as it's in there, you're going to get your answer. Okay? As long as it's smooth continuous. So here's example 5. Find the area of the region bounded by the graph of L sub x equal x cubed, the x-axis in the vertical lines, x equals 0, x equal 1. This is almost identically like the other one. It's just it's a different function. It's x cubed, not x squared. So you're going, and it's going from 0 to 1, not 0 to 2. So you're going from 0, 0 to 1, 1. Okay? And you're going to take a delta x here, which is 1 minus 0, 1 divided by n. Say again?
I'm saying, so 1 over n.
Yeah, exactly. 1 over n. Exactly. And then you could have taken the left, the end, or anything in between, that point right there. Whatever point you want from there, that's going to be it. So, they just say it's equal to 1/4. They don't tell you how they got that, but it is. Begin by noting that f is continuous, non-negative on the interval. Next, partition that into n subintervals, so it's 1 over n, just like you say, your delta x. Okay. According to the definition of area, you can choose any x value in that ith subinterval, any one, it doesn't matter. For example, the right endpoint will be fine. I times I divided by n. C sub I is equal to I divided by n. Okay? So that will then be I divided by n, C sub I divided by n. Okay? Then you're going to cube that and multiply it by that. Okay? Well, that would be 1 over n to the 4th, because this is cubed and that is the summation of I cubed. Well, you've got to go back and look and see what your summation of I cubed is. And there's what it is, 1 over n to the 4th, and that would be I cubed. That will have to be n to the 4th times n plus 1, n squared times n plus 1 squared, divided by 4, and the 1 over 4 on the outside, and multiply that through n squared, and when you square this, you have n squared plus 2n, n squared plus 2n plus 1. Pull the 1/4 out there with the n to the 4th, because you the 4. Yeah, pull that on out too, and that gives you what I was. Okay. What I like to do is take the 4 on out there too. Be 1 over n to the 4th. And what you have here is n squared times n squared plus 2n plus 1. When you square that, okay, that'd be 1 over n to the 4th times n to the 4th plus 2n cubed plus n squared. Okay? And then you put that and you get n to the I left off my 4. I said write it and I didn't write it. Okay, 4n to the 4th. Okay. 4, I gotta slow down. N to the 4th over the 4n to the 4th plus n cubed over 2n 4th plus n squared over 4n to the 4th. When you multiply those through, that goes to 1, that goes to 1 over n, this goes to 1 over n squared, these go to 0, and you're left with 1/4. So that's where you had. Or the way they wrote it was this way, that's exactly what. They just skipped a bunch of steps to get here, but that's how we got to here. This goes to 0, that goes to 0. It's going to work that way every time. Okay? Now, there's your 1/4.
You okay?
Yeah, it's just a cough. I swallowed it wrong, I think. Okay, so the area of the region is 1/4. Okay. Please tell us there's an easier way to do this. There is an easier way to do this. In general, a good value to choose of the midpoint is going to be, to choose is the midpoint rule, which is C sub I is that. And it really doesn't matter, but that will be a perfectly fine one. So it's x plus x to the n plus I plus 1 plus x to the I, halfway in between those, over 2. Times it, and that's it. Okay. They just end it there. Example 6, they go into, it's a slightly different example. It's a perfectly good one. It's the same kind of stuff, but let me suggest to you, why don't you go to larsoncalculus.com, absolutely free website, and you'll see the interactive version of that problem worked out. Great thing to do. If you want to see that, go for it. Okay, example 7 is another one. This is taking delta y's, which is fine. There's not really any difference in it. An example 8 is an example of the midpoint rule, and rather than taking class time for it, because they all get into these, actually example 8 gives you, it doesn't have n in it anymore. It does, it actually tells you what to approximate, and when you wind up doing that, you get an approximate answer, and then you can guess what the total answer will be. But I don't think it's really all that instructive to do this. Let's move on and see how the real way we do these. But if you want to try homework exercises, do any of the odds 5 through 9. They're all 3 at, okay. For those that might be new to the book, I don't know if any of you are new to the book. I always, in every set of homework exercises, give you the odd numbers. There's 2 reasons for that. Number 1, the answers for the odd numbers are in the back. So when you do the homework exercises, you do them, get the answer in the back, you've done. You can either do more of those or move to the next group. And then again, it'll be odd number exercises. Now, if you don't get the answer in the back of the book, and you go back and work through it, and you can't see how to get that answer in the back of the book, then go to calcchat.com, another absolutely free website. And it shows you how to. It's tutorial help and worked out solutions for the odd number exercises. So you got it right there. Done. Okay? Now, in addition to those, any of these that have red letters by them, and when you see a group of them that have these little, these are given a name, and I don't know what that is. A what?
QR codes.
2R?
QR.
QR codes. Yes, sir.
Hey, just paying your visit. Hey.
All right. But not here for class.
I know.
All right. Well, good to see you. All right. Take care. He was in class earlier, and his sister was in a class this summer. She said, I'm going to tell him to come pay you, but they can't pay you. That's so sorry. That was something between him and her. Maybe he wanted to see me, but I'm not going to interrupt the class with it. If you got the QR code and you have a smartphone, you can just do on that, and you'll go right to this other site, which is called calcview.com. And there you see more detail in how to work out the ones that are in red. And there's only 1 per section. Some sections don't have any. Well, I'll still make the assignments. So here's what I say. Okay, you hear. First group, any of the odds 5 through 9, they're all 3 at calcchat.com. Number 5 is at calcview.com. Do any of the odds 11 through 15, they're all at calcchat. None of them are at calcview. Do any of the odds 17 to 23, they're all at calcchat. 21's at calcview. Do either 25 or 27, they're both at calcchat. 25's at calcview. Do any of the odds 29 to 33, they're all at calcchat. 33's at calcview. Do 35, it's at calcchat. Do 37 or 39, they're both at calcchat. 39's at calcview. Do any of the odds 41 to either 41 or 43, they're both at calcchat. 43's at calcview. Do 45, it's at calcchat. Do any of the odds 47 to 55, they're all at calcchat. 49's at calcview. Do any of the odds 57 to 61, they're all at calcchat. 57's at calcview. And do any of either 63 or 65, they're both at calcchat. 65's at calcview. There's a couple of exploring concepts. You can play with those if you want to. They may be at calcchat. I don't know. You don't have to worry with them if you don't want to. 71's another kind of problem. You can do it however you want. You can skip it if you want to. It's a little more involved, but it's a calcchat also, or should be. 73 is a calc chat. It's just a true-false question, but it'll be described a little bit better there. 75 is a writing exercise. You can do it if you want to. You don't have to. 77 is a practical problem, seating capacity. You can do that if you want to. But those upper levels is just whether you want to or not. All right. So let's end 4.2. We're not quite ready to get to the easy way. Got one more little hurdle here, and these are called Riemann sums. And if you find these look an awful lot like we were just doing, that's what they are. They're a further example of what we were just doing. So let's go from current slide, and hopefully we'll be through this really quickly. Well, I don't do anything really quickly. Riemann sums and definite integrals. Let's understand the definition of a Riemann sum, which, by the way, folks, Riemann was a person. You see a picture of him in your book there. Georg Friedrich Bernhard Riemann. German name, isn't it? Yep. You could write your paper on him, or how he came up with Riemann sums, or how they applied, or anything such as that. Leave that alone for now. We'll evaluate definite integral using limits and geometric formulas, and we'll evaluate definite integral using properties of definite integrals. Hey, looks like we're going to get there this time. So let's first talk about Riemann sums, and if this looks familiar, it should be, okay? Here's our partition. Now this time, we're partitioning the subintervals with unequal widths. And frankly, I don't see why they do this, but they do, and it works perfectly fine. Let's consider a region bounded by the graph of f of x equals square root of x, and the x-axis from 0 to 1. Certainly it's positive from 0 to 1. Here it's 0, 0, there it's 1, 1, and it's something else in between. Always positive. And we want to evaluate the limit as n goes to infinity of the integral, the summation from n equal I equal 1 to n f ci delta x of I. Just like we did before, with the only difference is our delta x of I is not a constant. Okay? C sub x of I is going to be that right endpoint, fine, of the partition given by, and here, why in the world would you choose this as a partition? Actually, it makes the calculation easier. That's about the only reason. C sub I is equal to I squared divided by n squared. As long as I is between 0 and n, or 1 and n, that's always going to be a number between 0 and 1. Okay? Delta x of I is the width of the interval, of the ith interval, and that's given by well, they don't actually give you the formula except that it is from one of those to the next one. It's a variable width. Okay. The key here, guess what we're going to do? Let n go to infinity, so no matter what the width is, they're all going to 0. Okay? All those partitions are going to 0. So they just go at different time, spaces. So your partition here is 1 over n squared, 4 over n squared, 9 over n squared, whatever. You're doing, and you're letting that go as long as you, the n is large enough so that it stays less than 1. Okay? Those don't have equal widths. Okay. So, the width of each interval, here it is. The delta x of I is I squared over n squared, that's the right endpoint, minus the left endpoint is I minus 1 squared over n squared. And if you expand that top one, this is so much. I squared over n squared minus, this would be I squared minus 2I plus 1 over n squared. And this would be I squared over n squared minus I squared over n squared plus 2I over n squared plus 1 over n squared. Okay? Well, the minus times minus, I missed the last one. I got the first one right, but missed the last one. This is a minus here. Okay? Okay. Yeah, the minus here changed this to a minus, that to a plus. It should have changed that to a minus too. Okay? So, what we see, these two go out, and then what you have is just 2I over n squared minus 1 over n squared. So that's the width of the interval, which you could call 2I minus 1 over n squared, if you wanted to do it that way. Okay, there's the width of the interval. Okay? Got it? Okay. So I'm going to erase my chicken scratch there and see what they wound up with. Yeah, 2I minus 1 over n squared. Okay? So the limit is f of the ci, and you can pick any value you want there, and they said let's choose ci being I squared over n squared. Remember they said that early on. This is your delta I, which we just calculated here. And the square root, see, here's the advantage of choosing this as the thing, because the square root of I squared over n squared is just I over n. So clever of them to choose that one. And so that would just be, and if you look at that then, this will be I over n times this. So you got 1 over n cubed out front, and this would be 2I squared minus I. It's what's left under there. That's your 2I squared. What's that?
After you get out, and you have to do the descriptor. After you take the square root.
Yeah, because this is square root of I squared is I, the square root of n squared is n. Yeah. So that's where that went. And that's why they chose that. It seemed like a weird thing to choose at first. Is it really raining outside? Or is it just foggy?
It's sort of hazy.
It's what?
It's just sort of hazy.
Hazy, okay. Because I left my windows cracked because I didn't think it's supposed to rain today, is it?
No chance of rain.
Okay, good. Huh?
There's no
Okay.
chance of rain.
Okay. Well, I was going to say, that's scary. I'm going to have a wet end going home. Okay. So, that's how you get 1 over n cubed, summation of that. And then you go back and do your 2 times I squared, which was, what was that? N times n, 2n minus, over 6. Those same things we've done before, n times n plus 1 times 2n plus 1 over 6 minus that, and you go through all the same mess we did before, and you just have to, I hope you are used to doing the math, multiplying these out, stuff like this, subtract combining like terms. It's just really tedious. But again, remember the 1 over n cubed comes out front. Well, they don't even do it out front. They just do it like this. And then looky here. That would be 2/3, right? 4 over 6, because the n cubes go away. Then this is n over 1 over n. This is 1 over n squared. Those are both going to go to 0. This n goes to infinity. So your answer is 2/3. Okay? Just like we did before, only we picked some weirder partitioning. Okay? So it's going to be 2/3. That's your answer. Okay. So it's just sort of like we did before, only we don't have even intervals anymore. Okay? We know that the region shown here has an area of 1/3. How do we know that? Because the region under here was 2/3, wasn't it? And 1 to 1 to 1 to 1, that's a square of 1. So that's going to be an area of 1/3. Okay? So, what is this telling us anyway? I don't know. It's just interesting. Because the square bounded, is area of 1, you conclude the area of the region is 2/3 under there, 1/3 out of there. Okay? And you got those by uneven intervals because it made the problem work easier doing that way. Okay, this agrees with the limit found in example 1, even though that example used a partition having unequal widths. The reason that particular partition gave the proper area is that as n increases, the width of the largest subinterval also approaches 0. So that's the key. As n goes to infinity, even the biggest subinterval is going to go to 0. So it's all. This is a key feature of development of definite integrals. Okay, it's heading those. The delta x's are always going to 0, just like in differential calculus, the denominator was going to 0. Can't do it, but as it approaches it, that's where we're going. So here's our Riemann sum. Definition of Riemann sum below. Note that the function f has no restrictions other than being defined on the interval. It doesn't have to be continuous. It doesn't have to be positive. It just needs to be defined. Woo. So, let f be defined on some closed interval a to b. Let this thing we're just going to call a delta. It's not delta something, it's just a delta. And sometimes I actually call that a del, but that's usually reserved for something else. So let that delta be whatever the partition of a to b is. Whatever it is. It can be uneven, it can be any kind of partition you want. It just needs to be the a is less than, no, a is actually equal to your left endpoint, 8x of 0, and that's less than the next one, next to the next one, less than the next one, until the final one, x of n, is b. You got n subdivisions, but they don't have to be equal length. The delta x of I between any two of those, the width is that subinterval. Delta x of I is the width of the subinterval from x of I minus 1 to x of I. Okay? C sub I is any point on that subinterval. Doesn't have to be the midpoint. It could be. Doesn't matter. Any point on that. Then the sum of all those things, this is definition of Riemann sum, summation I equal n, 1 to n of f of C sub I times the delta x of I as delta of x of I minus 1 less than or equal to C sub I less than or equal to x of I. That's called the Riemann sum for any partition del. Again, you don't have to have continuous functions. You don't have to have positive functions. Just any old function. That's going to be your, that summation is going to be your Riemann sum. Just like we did before, only less restrictive. Doesn't have to have equal interval. So the width of the largest subinterval of that partition del is called the norm. Y'all don't remember Cheers, do you? When Norm walked in there, I went, Norm! You know, so that's what they're saying. The largest subdivision. No, that's not what they were saying. Okay, but anyway. The norm of the partition is denoted by double bars around the del. Whatever the largest partition is in that is called the norm. If every subinterval is of equal width, okay, then the partition is regular, and we already talked about those. That would be b minus a over n. But it doesn't have to be. Okay, that's a regular partition. The general partition is just anything there. Okay? For a general partition, the norm is related to the number of subintervals in that, in this way. Let's just take this and multiply by n, divide by the norm. Okay? And then you get this. Okay? Because you know this is greater than or equal to any of the subdivisions, so when you divide by that, this is now, because this is the bigger piece, that's less than or equal to n. So what? I mean, okay, it's fine. The n's going to go to infinity anyway, right? I'm sorry. Am I going too fast? time to catch up here. Please, if I go through a slide before you're ready for me to, let me know. Okay? All right. So the number of subintervals in a partition approaches infinity. Who cares what the norm was? It's going to 0, okay? They all have, it goes to infinity, even the biggest one's got to go to 0, okay? That is, the norm approaches 0 implies that the n is going to infinity. The converse of that statement is not always true. If the norm of some interval I'm not sure what they're saying here, wait. And what difference does it make anyway? I guess what they're saying is this is not always going. Have they defined what this means? I guess that's a partition of any thing, and that's not always. Looks like to me it is going to infinity, but it's going that way, not this way. That may be what I don't know. But I don't think it matters any. Okay. It's shown, did you need that? Okay. It's shown in this figure down here. For any positive value of n, the norm of the partition is 1/2. Oh, they're back on that. Okay. So letting n approach infinity is not force the norm to approach 0. That's what they're saying. Okay. I was looking at this end, they were looking at the other end. In a regular partition, however, the statements that if would be true in any kind of regular partition, which is what we're going to deal with basically. Okay. So why did they even bring that up? I'm not sure. Okay. And there's Riemann talked about that kind of thing. Now we really get where we're wanting to go. Definite integrals. To define the definite integral, let's consider the limit. The limit as your norm is approaching 0 of the summation I equal 1 to n. Now this implies n is going to infinity, remember? Of f of c sub I delta x of I, that limit is going to exist. Consider that limit. To say the limit exists means there exists a real number L such that for every epsilon greater than 0, this is a good old limit thing again, there exists some delta greater than 0 such that for every partition in which the del is less than the delta, the norm is less than that little delta. See, this is a capital delta, that's a little delta. It can be really confusing. So let's just call this norm. The norm is less than delta. It follows that the absolute value of the difference between L and this is going to be less than the epsilon. So no matter how small an epsilon you want, you can find a delta, a norm less than that delta that guarantees this is true, no matter how small you choose that epsilon to be, regardless of the choice C sub I that you do on that interval. Okay? So just keep picking smaller and smaller norms as long as they're positive, and you can find one that'll work. That's if the limit exists. So here's the definition of definite interval. F is defined on the closed interval A to B. All it needs to be defined. And the limit of the Riemann sums over the partition delta. The limit is that norm of that partition approaches 0 of that summation F of C sub I delta x. Okay? That limit exists, as described earlier, then f is said to be integrable over the interval a to b. Okay? Now here's what you've done there. That limit of this summation, the summation becomes an integral, and the limits of the integral are from a to b. Your f sub x, f sub ci, these are values of x here, so that becomes your f of x, and your delta x becomes your dx. In other words, the limit as this goes to 0, the delta x is getting smaller and smaller, and it becomes a dx. That's exactly what we called it in differential calculus. As the delta x is going to 0, you wound up with df dx. That was your limit. And these were some values of x, so just do f of x dx. Okay. That limit is called the definite integral of f from a to b. Number a is the lower limit of integration, number b is the upper limit. You're integrating from a to b. You're summing all those from a to b. That's what you're doing here. Okay? So, the Riemann sums were defined for functions with very few restrictions. A sufficient condition for f to be integral on AB is that it is continuous on A to B. That's all you need. Okay? Doesn't always have to be positive, just so it's continuous. The Riemann sum didn't even have that, but we do require that for it to be integrable. So continuity implies integrability. But again, integrability doesn't always imply continuity. So we won't go the other direction. If the function f is continuous on some closed interval a to b, then f is integral on a to b. That is, the integral from a to b of f of a dx does exist. Now, f of 1 was way back at the beginning, so we haven't skipped anything. Now, here's where things gets a little squirrely. We spent so long with all those sums and lowers and uppers and stuff like that, you probably forgot what your antiderivatives were, didn't you? But we did those, remember, in 4.1, didn't we do antiderivatives?
Yeah, it's called to undo derivatives.
What's that?
Undo derivative.
Second?
You gotta undo derivative.
Yeah, it undoes a derivative, and that's what we did back in 4.1. Antiderivatives in indefinite integrals. Now we're going to do definite integrals, but we're still doing antiderivatives. Remember, nothing has changed there, except we've got limits on it. So let's evaluate that. What would be the antiderivative of 2x? X squared. So that'll be x squared, but we're going to evaluate that from minus 2 to 1. Okay? Now, what do we really mean by that? And I feel like we're jumping off onto here. Oh man, they're going back to the integrals. I mean, to the Riemann sum type thing. I guess we have to do that. Man. I'll come back and show you what this is later. Okay? Let's do it the way they do it now. The function f of x is 2x is integrable because it's continuous. Okay? But we're going from x equal negative 2 to x equal positive 1. Well, at negative 2, this thing is a very negative number, like negative 4. And at 1, it's a positive number, too. So this has some area down here below the x-axis and some area up here above the x-axis. And what you're going to see is that these negatives subtract away from the positive. You're going to wind up with a negative answer. And we usually don't think of areas as being negative. But in this case, it is. Moreover, the definition of integrability implies that any partition whose norm approaches 0 can be used to determine the limit. Okay? So let's just take our For computational convenience, define your partition by subdividing that into n subintervals of equal width, just like we did before. B minus A, 1 minus or minus 2 is B minus A, 3. Minus or minus 2.
Minus.
So 1 minus or minus 2 is 1 plus 2 is 3 divided by n. Okay? We're going to do equal subintervals. So you get 3 over n. Okay? Oh man, I thought we were through with these, but we're not. Okay? We're going to do this one this way. Okay? So, choosing a C sub I as the right endpoint. It doesn't really matter, but we'll choose that. And that would be A plus your I delta x. And your delta x is 3 over n. So that would be minus 2 plus I times 3 over n. So there's your C sub I, your right-hand endpoint for every one of those subintervals. Okay? Goodness. My eyes are itchy. So here's your definite interval. You're going backwards with it now. Here's your definite interval. We're going to make it into a Riemann sum. Only this is variable, so del is approaching 0. The summation I equal 1 to n of that thing there. And we just said what that was going to be. Well, we sort of said. Alpha C I would be, remember it was 2x. Alpha of x is 2x, so it's just going to be 2 times C sub I. Well, it's the partition going to 0 means n is going to infinity. Okay, so the summation of that, they just flip that around to mean that. And that would be 2 times, and what was your C sub I? Remember it was minus 2 plus 3 I over n. And then your delta x is 3 over n. Boy! They don't give up on these in a hurry, are they? Okay. So this is going to be minus 4 plus 6 I over n times 3 over n. So it's minus 12 over n plus 9 I over n. Okay. So how did it get a 6? Okay. Okay. Why they did it this way, I'm not sure. So they pulled out the 2 and the 3 over n. That gave you 6 over n out here. Leaving you in here a minus 2 plus 3i over n. Okay, fine. We'll do it that way, okay? So that'll be the limit n goes to that. So basically, they take the minus 2 outside the summation and just leave a 1 there. So that's what the first part does. And then they pull the 3 over n outside the summation and just do the summation of I. Okay, we know what both of these are. This is just n, right? The summation is n, and this one's n times n plus 1 over 2, or something like that, right? So we'll plug those in. So minus 2 times n. Okay, so we got limit n approaches infinity of 6 over n times the minus 2n, yeah, plus 3 over n, that's on the outside, n plus times n plus 1 over 2. So they're going back to doing all this stuff again. I'm so sorry. Okay? That summation there is n, right? Multiply negative 2 times. Okay. Now, I can believe it if you don't want to believe this, but let's do what's in here first. Minus 2n. Oh, let's multiply this. It's n squared plus n. Okay? Wait, easier than that. Just cancel out the n's here, okay? That's nice. So it'd be minus 2n plus 3n plus 3. If you put this over 2, that would be minus 4n plus 3n plus 3. Minus 4n plus 3n is minus. They skip so many steps and drive me nuts. Let's do it. Okay. This one right here, I'm going to leave off the 6 over n, the limit is in front, times minus 4n over 2. I'll make that minus 4n squared. No. Let's just get rid of that n. Okay. So minus 4n over 2 plus 3n over 2 plus 3 over 2. Right? I believe I did that right. Okay? And that's going to be minus 24n over 2. So that's a minus 12. Right? And this will be plus 9. Okay? Because the n's go out. The 2 will go into 6, 3, 3. So that's plus 9. And then this will be plus 2 will go into 6, plus 9 over n. Yeah, and that's what they got. Okay? So this will be minus 3 plus 9 over n. Limit is n goes to infinity. That goes to 0. That gives you minus 3. Okay. There we have it. Minus 3.
How can you have a negative area?
Yes, that is the question. Here's the picture. Because the definite integral in example 2 is negative, it does not represent the area of a region shown in figure 421. Okay? Well, here's what's happening. Remember when we defined this, this is a positive thing because this is 2n minus 1, minus 0, okay? 2x minus 0. This is a positive area here. But this is 0 minus 2x, okay? So this is a negative area. So when you add the little positive area to a big negative area, you get a negative area. Well, negative areas, you can't really have a negative area, but it's the opposite of that area. It's the negative of that area that you're doing there, which can be then a negative number. The area is positive, but the negative of that is negative. So your definite integrals can be positive, they can be negative, they could be 0. If you extended this on up to here, then the same area here, positive, would equal that area here, that whole area would be 0. So if you went from minus 2 to 2, area is 0, which is, you don't think of areas as either being 0 or negative. So don't think of them as an area anymore. Think of them as a result of your integration. Okay. Now, yeah, I was jumping the gun on you. I realize now. So the definite integral as an area of a region, if f is continuous and non-negative, now they're making it non-negative on a closed interval A, then the area of the region bounded by the graph, the x-axis, and those vertical lines, is exactly that, if this f is non-negative. If that f becomes negative, though, then you've got another issue on your hand. But as long as that's true, then that is an area. If it goes negative, then it's not an area. It's the sum of a area plus the opposite of an area, which then could be negative. As an example of theorem 4.5, consider the region bounded by the graph of f of x equals 4x minus x squared, the x-axis, and shown here. Okay? Now let's just check and make sure they've got a few points right. Would 0, 0 be right? X equals 0, 4 times 0 minus 0, that's 0. So that works. And when x equals 4, It'd be 4 times 4 is 16 minus 4 squared is 16. Yeah, that's 0. And it looks like your max would be about 2. That would be 8 minus 4, 2. So, yep, that would be 4. Yeah, looks like they drew it right. Okay? So that's your parabola. Okay? And you want to do so f is continuous, f is non-negative on the interval 0 to 4, and the area would be that thing. And I'm sure they want us to go through and do a summation of it. And I'm sick and tired of doing the summations. I want to get straight to the integrals. Okay? You can evaluate the definite integral in 2 ways. You can use a definite limit definition. Yes, I want to do that one. Or you can check to see whether the definite integral represents the area of a common geometric region, such as a rectangle, triangle, or semicircle. Well, that's not none of those. My word. They say sketch the graph of each of these, evaluate each integral using a geometric formula, not using the others. And you tell me how to graph f equal 4. Yeah, that's it. F equal 4 would be like this. If you evaluate that from 1 to 3, you have a rectangle. 4 by 2. Do you buy it? Okay. How about this one? The integral from 0 to 3 of x plus 2. Okay, well, this is a straight line with a y-intercept of 2, and let me go back and draw this more smartly. Oh, it didn't take. Okay. That's not very pretty, but it'll do. When x equals 0, y is equal to 2, and it's going to be a straight line with only 3, so it's going to be there, there, there. Does everybody buy that? Straight line, slope 1. Okay, you're going from 0 to 1. Okay, now that's what we call a trapezoid. Remember that one? 2 parallel sides and 2 sides that are not parallel. And how we determine the area of that is by taking it and flipping it across the diagonal. Okay, that'll give twice the area, right? Okay, so we'll go up this has gone up, this point here is 3, 5, so you've gone up 5 from here, and this is 0, 2, so go up 5 from that. You want 2, let's see, 3, 4, 5, 6, 7, so we'll go to here. Okay, so you take this area, flip it over like that to that area, and what do you got? You got a height of 7 and a width of 3. So 7 times 3 is 21. Take half of that, and you got 21 halves. So this area right here is 21 halves. I think. I did it fast. But the formula is add the two sides, 2 plus 5 is 7, times 3 is 21 divided by 2. This one might be a little confusing looking at first, but I think you know if you were to draw it. Anyone know how that looks? Okay, your x is going from +1, -1, okay, like this. And your function is always positive, right? And when you put a -2 in there, you get a 0. You get a +2 in there, you get a 0. You put a 0 in there, you get a +2. Guess what's that a picture of? Half a circle. And what is the area of a circle? By r squared. What's your r in this case? Which is, what's the radius of that circle? 2. So, and you got half of that, so it's 1/2 pi times 2 squared, which would be 1/2 of 4 pi. So this would be 2 pi. All right. That's what I think they are. Let's see what they are. Are we running out of time? Oh my goodness, how could that happen? Let's just do it quickly. That's a rectangle, area 8, we got that one. 21 halves, we got that one. And 2 pi. Isn't that what we got? Okay, good. All right. Where were we? Okay, we'll start with the slide at the bottom of page 274. Homework exercises here. Do number 3. It's at Calc Chat and Calc View. Any of the odds 5 through 9, they're all at Calc Chat. 7's at Calc View. Try doing number 11. It's at Calc Chat. Any of the odds 13 through 21, they're all at Calc Chat. And do any of the odds 23 to 31, they're all at Calc Chat. 25's at Calc View. And then I think we'll pick up the rest of those next time. All right, good deal. All right, sorry, we ran out of time awfully quick today, it seemed like. Okay. I'm sorry. What's that?
I was just saying, time flies when you're having fun.
Yeah, it really does. And we will, we're really close to really doing integration. So as soon as we can get through this next little bit, we'll be ready to go on integration. I didn't want to spend too much time with these sums because it's all algebra and it just takes a lot of time. When we get into the real calculus of it, that'll be much better. All right, good deal. We'll see you on Wednesday.